Hi, I'm Prof L and welcome to Chemistry Matters. And today we are going to be talking about another way of making models of organic compounds, or at least looking at organic compounds in 2 dimensions. So essentially we're going to be squashing 3 dimensions into 2 dimensions and utilizing that to look at the structures of a particular class of organic compounds, of which I'm sure you've heard, carbohydrates. Carbohydrates, very important class of organic compounds. Okay, so otherwise known perhaps as sugars. Okay, carbohydrates, as the name suggests, they're made up of carbon, carbohydrate. What do we know matches with hydrate? Obviously water, okay? And so therefore, we can think of these carbohydrates as being made up of carbon and the elements of water, which are hydrogen and oxygen, okay? So, what's so special about carbohydrates? Well, there's a whole bunch of carbohydrates out there in chemistry and biology, very, very important in biological systems. And of course, we couldn't get by without our sucrose because that makes life sweet. So, sometimes we use the words sugars and carbohydrates interchangeably. Sometimes that's correct, sometimes it's not truly correct, but anyway, we'll use the term carbohydrates, hopefully wherever possible. Right, so just when you thought you knew all the nomenclature systems that were possible, we are now going to introduce another one, okay? Another way of depicting 3 dimensions in 2 dimensions, 3-dimensional molecules on a flat surface. And this dates back to a guy by the name of Emil Fischer, German professor, great organic chemist from late 19th century, early 20th. And his work with a molecule called glyceraldehyde. Okay, so glyceraldehyde looks like this. Okay, CHO there, HOCH2 there, and an OH there. Okay? Glyceraldehyde, probably because it's derived from a molecule called glycerol, which has 3 carbons, bam, 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 just like this one. Now, let's have a look at the structure of this, and hopefully your trained eyes, after having looked at the previous videos, should be able to figure out that, yep, we have got a stereocenter in this molecule, and that stereocenter is this puppy right here, this carbon here, because what's it got around it? Well, it's got an OH, it's got a CHO, and it's got a CH2OH. So, and also, obviously, a hydrogen, an implicit hydrogen on here as well. So therefore, we've got 4 different groups around that carbon, so that makes that a stereocenter. Okay, that's great. So what? Why is this particular molecule special? Well, let's draw the 2 possible enantiomers of this particular molecule now, and we're going to draw them for no apparent obvious reason like this. So we're going to have CHO there, we're going to have CH2OH there, we're going to have OH out here, whoops, and we're going to have H like so, okay? And its mirror image we are going to draw in the same sort of idea like so. So this is going to be HO, this is going to be H, and this is going to be CH2OH. Okay, so those are the enantiomers of glyceraldehyde, and this one happens to be the R enantiomer, and this one happens to be the S enantiomer. If, again, you go through and do your little thing, and again, you can never have too much practice with this stuff. Assigning R and S enantiomers It's good practice, and again, if you can get to do it without having to use chemical model kits, and you can do it in your head, then you are well on the way to becoming an organic chemist, believe you me, okay? So, why have we chosen that way, that particular way to draw them? Because usually it looks much better if we draw 3 dimensions like that. It really does. It just looks a lot better to me. So you would write CH2, CH2OH, let's say, and you'd have an H and an OH like so. It just looks nicer. But we're going to write them like this. So what that means when we do that is that we don't have 3 atoms in the same plane anymore, as we do when we draw it like that. That carbon, that carbon, that carbon, they're all in the same plane. It just makes life easier. But Fischer said, no, we're going to do it this way. Okay, so this is a 3-dimensional drawing, remember, in 2 dimensions. Okay, now Fischer said, okay, I need to come up with a way of depicting 3 dimensions in 2 dimensions, and I kind of don't want to have to go to the hassle of drawing all of these sort of hashes and wedges and things like that. In fact, that might even have not have been around in his day. This could have predated that because it was a wee while ago. So what he said was, okay, I'm going to orient this molecule in a particular way, and then essentially what I'm going to do, I'm going to take this 3-dimensional molecule that I've oriented essentially like this, and I'm going to squash it flat onto the page. So I've oriented the molecule so that these guys here, this one and this one, are pointing away, and these guys here out the side are pointing towards me. And I'm going to flatten out the whole thing. I'm going to squash it flat, and when I do that, what I'm going to get is something that looks like this. CHO, CH2, OH, and we're going to have the OH that side, we're going to have the H that side. The enantiomer is going to look like this. CH2, OH, like that. We're going to have HO, and we're going to have H. Okay. And so you might think, okay, well, these still look like mirror images. If you draw a mirror down here, then yep, that's going to map to that, that's going to map to that, even though now what we've got is a 2-dimensional representation. We don't even have to worry about the whole 3-dimensionality of the thing. We've converted, we've basically taken the 3-dimensionally out of it, seemingly, but it is implicit there because there are some rules when it comes to drawing Fischer projections. So the rule number 1, when you're drawing a Fischer projection, you put your most oxidized carbon at the top. By the most oxidized carbon, generally we mean the carbon bearing the most oxygens, but you can see that this carbon has 1 oxygen attached. This carbon also has 1 oxygen attached, but this is a C double bond O. And this is a C single bond O. This is more oxidized than that, okay? It's not a great rule, that, because sometimes you've got to try and think and figure out, right, what do we mean by most oxidized carbon? So we orient the most oxidized carbon at the top, okay? And then what we are going to say is that bonds that are vertical are going away from you. So you imagine any vertical bond is being pointed into the board, is going away into the board, and any horizontal bonds are coming out towards you, okay? So therefore these are coming out of the page at you. And that's what we've done. We've taken the 3-dimensional representation and squashed it flat into 2 dimensions, okay? So, great. Okay, so why was this important? Okay, so again, another little bit of history. When Fischer was around, I guess one of the methods that they had to look at enantiomers and optical activity or chiral molecules was polarimetry, okay? So that was around at that stage. So they knew whether particular molecules rotated the plane of polarized light to the left or to the right, or plus or minus as we now call it these days. Okay. But what they had to do was figure out what's the configuration. Okay. And they didn't call it R or S in those days. The R and the S were relatively recent, probably 20th century invention. Prior to R and S came, dare I say it, D and L, okay? And this is where confusion starts, okay? Sugar chemistry, boy, if you're going to be a sugar chemist, you've got to be a special type of person, in my view. Fischer labelled this particular enantiomer of glyceraldehyde the D enantiomer, and he labelled this particular enantiomer of glyceraldehyde as being the L enantiomer. Now, this was not arbitrary. He called this one D because, here we go, the OH on the penultimate carbon in the longest carbon chain was on the right-hand side of this projection. Okay, D, I think Latin for dextro, which is right, I believe, and L, Latin for levo, meaning on the left. So this enantiomer was called the D enantiomer because of the position of this OH on the penultimate carbon. Penultimate means last but one. So this is the last but one carbon in the chain. We go from the top all the way to the bottom, and as we approach the bottom, this is the penultimate carbon. The OH is on the right, so we call this the D enantiomer. Okay? And in this case, we go from the most oxidized carbon down to the bottom. The penultimate carbon occurs at this intersection here. And just remember, in a Fischer projection, every intersection is a carbon. So that's a carbon there. The OH on that penultimate carbon is on the left-hand side. And so therefore we call this an L enantiomer, okay? And it so happens that the D enantiomer has what we call a specific rotation. It rotates the plane of polarized light plus 13.5 degrees, and with that one we go minus 13.5 degrees, okay? Now, again, the D and the L and the plus and the minus are not related, okay? They're not related, just the same as the R and the S and the plus and the minus, they're not related. So don't get mixed up with that. Okay, so what? So why is glyceraldehyde so special? Well, glyceraldehyde is the first, probably the simplest carbohydrate, if you want to be sort of technical in that term, okay? And we'll see what we mean by carbohydrates in a minute, okay? So, what Fischer did was to relate the configurations of all sugars back to the configuration of this molecule here, glyceraldehyde, D-glyceraldehyde and L-glyceraldehyde. Now there's quite a lot of carbohydrates, quite a lot of sugars out there, okay? And as I said, that's what Fischer did, okay? So basically, that's why this is a really, really, really important molecule, okay? D-glyceraldehyde because of the positioning of that particular OH on the right. L-glyceraldehyde because of the positioning of that particular OH on the left, okay? And that is the system that he used, as I said, for all sugars, for all simple sugars, all simple carbohydrates. Okay, so how many simple carbohydrates are there? Well, as this shows, there are a few, okay? So let's have a look at this in a little bit of detail, okay? Because understanding this slide here, or this picture here, really is central to understanding carbohydrate chemistry, okay? If you don't get this, then carbohydrates going to be a real, or the carbohydrates are going to be a real slog for you. Okay, So, sugars. What type of molecules are sugars? They're basically molecules that contain carbon chain of C3 to basically C6, pretty much, okay? And they often contain an aldehyde or a ketone and an alcohol, and in fact one or more alcohols. And we have obviously chiral centers, we have stereo centers in these, okay? So we name sugars as either containing aldehydes or ketones. So if the sugar contains an aldehyde, we call it an aldo, okay? Now, the word "-ose" or the suffix "-ose" means that we're talking about sugars, and tetra means 4, okay? So I said, remember counting in chemistry that we've got eth, meth, bute, sorry. Now, in this case, we go tet meaning 4, pent meaning 5, hex meaning 6. So here is an example now of an aldotetrose, And this aldotetrose here, so a tetrose means it's a sugar with 4 carbons, a 4-carbon chain, 1, 2, 3, 4, okay? Now on that carbon chain, at the top, we're going to have an aldehyde. That's the aldo bit. At the bottom, we're going to have a CH2OH, like every other sugar, okay, like every other simple sugar. And at the intersections, or I guess at the intersections of these lines, we're going to have stereocenters. So in this case, we're going to have 2 stereocenters, and they come from the fact that on each of these carbons in the middle, we've got an OH and we've got an H. And so that makes the whole, that makes that carbon there a stereocenter, it makes that carbon there a stereocenter. And so therefore, this is going to be an enantiomer. Okay, this is certainly a stereoisomer, and in fact, this will have an enantiomer. It will have a non-superimposable mirror image. Now, this sugar has the name erythrose. We're not going to discuss where that comes from, but we look at its stereochemical descriptor. It's D-erythrose. D-erythrose because on the penultimate carbon atom, the one that's next door to the CH2OH, we've got an OH and it is on the right. Okay? So that's D-erythrose. We can draw the mirror image of that. That would be L-erythrose. Okay? We have another way of arranging the H and the OH in the stereo centers, and that would be like this. Okay? We're now on the Fischer projection. We've got this OH on the left, but this OH is still on the right, okay? And so therefore, this is D. This is a D sugar, and again, this has a special name. This is called 3-O's, D3-O's. So we've got D-erythrose, we've got D3-O's. Each of these has got a non-superimposable mirror image, and so we've got 2 stereocenters, 4 possible stereoisomers from that, okay? If we extend the carbon chain by 1, then what do we get? We get an extra group of OH and H. It's an aldopentose. Now, aldo meaning an aldehyde at the top, O's meaning it's a sugar, pent meaning we've got 5 carbons in the longest chain, okay? So, here is a molecule you may have heard of, ribose, okay? D-ribose. It's D because there is your penultimate carbon, the OH in the Fischer projections on the right. Arabinose, xylose, xylose and lyxose, okay? They all have got that penultimate OH on the right, so they are all D sugars. They will all have non-superimposable mirror images. We've got 3 stereocenters, okay? And so 2 to the power of 3 is 8. We will have, as I say, non-superimposable mirror images of all of those, so that makes 8, okay? Stereoisomers. And then we get to the aldohexoses, which now have got 6 carbons in the chain. So these 4 central carbons are all stereocenters. They've all got H's and OH's on them. Allos, altros. Here's the one that you absolutely will have heard of, D-glucose. Okay? This is called D-glucose because the OH on the penultimate carbon is on the right. And if you look at the configurations of all of these 4 central carbons, on all of these, they're all different. And so that gives us 8 D sugars, each of which will have a non-superimposable mirror image, and so that gives us 16 stereoisomers, which is 4 squared. We've got 4 stereoisomers, 4 to the power of 2, okay, sorry, 2 to the power of 4, sorry, is 16, okay? And so you can see that this is going to get quite complicated quite quickly. Thankfully, we don't really go much beyond these. Glucose, mannose you may have heard of, and the other one possibly galactose is one that you may have heard of. Okay, so this is your very, very gentle introduction to sugars. This is the whole D and L thing, which I really, really don't like. If I was going to be brutally honest, they should be expressing the configurations of each of the chiral carbons in sugars, but that's never going to happen because this is too ingrained, sadly. So just stick with your D and your L, okay? And remember, look at your penultimate OH, or the OH on the penultimate carbon, and see whether it's on the right-hand side or the left-hand side. If it's on the right, it's D. If it's on the left-hand side, it's L, okay? Right, we are going to have more of this because, by crikey, carbohydrates are holding all sorts of interesting things for us in the next video, okay? I will see you there, I hope, okay? Take care and see you later.